on our last topic for the test. It's called the mean value theorem. It's also has a little brother added onto it called Rolle's theorem. So here is what Rolle's theorem says first. So I'll hide that one. Do that guy there. Rolle's theorem says that if you have a normal continuous differentiable function from A to B, and the value of the function at A is the same as the value of the function at B, so it starts and finishes at the same height. So you can imagine a function at A starts at this height, then it does some stuff, and it finishes B at the same height. Then there's guaranteed to be at least one number C between A and B where the derivative is 0. Does that seem intuitively kind of obvious that if a function starts at one value and it finishes at the same value, that it has to be at least 0 once, right? Because if it goes up, doesn't it have to come down? And if it goes down, doesn't it have to come up? And that up, down, or down, up is going to generate a 0. And in this very small picture I've got here, there'd actually be 3 places, wouldn't there? There'd be one there, and one there. So there are 3 possible places, and that is called Rolle's theorem. So what do you get to do as homework for things like that? Well, let's show you what question 3 looks like. You'll be given a function, typically. This function is that guy, that guy, that guy, and that guy. And the interval that they're talking about is from -4 to 4. So, go through a hit list in no particular order. Would you agree that this function is continuous from -4 to 4? And I'm not proving it, I'm just saying it's a cubic, right? It goes up and down. Aren't all cubic functions, all polynomials continuous? So 1 is continuous. 2. Would you agree that you can differentiate this function and there won't be any funny vertical asymptotes or places where you can't differentiate it? So we're just going to assume that that's also true. So it's differentiable. I'm going to find the value of the function at -4, and I'm going to find the value of the function at 4. And oh God, what's this fill equal to? Let me find out. And if you plug -4 in here, you get, I've got the answer in front of me here, you get -61. So what does that mean? That means you can use Rolle's theorem. So that guarantees that somewhere there's a point whose derivative is 0. Now, if I differentiate that guy, I can actually find him, which is typically the last thing they expect you to do. So if you differentiate that guy, you get 3x squared. That guy, you get -8. That guy, you get 16 equals 0. I'd probably pull out a 3 here. No, I won't. I just realized 8 doesn't work with that. So I'll just factor it then. What am I looking for? Oh, well, I'm looking for a 3x and an x, that's for sure. And I'm looking for a plus and a minus. And what am I going to look for? 2. 4 and a 4. 4 and a 4. There we go. Double check it. 3x squared minus 12 plus 4. Nailed it. So that's one of the places where the derivative is 0. This is the other location where it is 0. And they're asking us, pardon me, they're asking us to find a value such that the derivative is 0, and the one they want is that. I guess they could have used that one because it is technically an interval, but Rolle's theorem says you got to keep away from the endpoints because you can never be 100% sure that the other side is differentiable. So you basically just do, where is it? Between A and B, not allowing yourself to equal the endpoints. So that one there essentially gets ignored. And so there's only one answer. So almost like you're not doing anything really. What you're getting is a function and you're finding out if you can differentiate and if it's continuous. And is the value of the function at the start of the interval the same number as the end? And if all of those things are true, then you can use Rolle's theorem. And Rolle's theorem says this function is equal to 0 somewhere in that interval, right? This function's derivative, I should say, is 0 in that interval. And then you go and solve and you find it. That's essentially what Rolle's theorem gets us to do. So this one is like question 5. In this question, a lot of what we're doing, we're just going to say yes. Would you agree this function is continuous in the interval -3, -1 to 3? Right. Would you agree that this function can be differentiated in that interval? Yeah. Is the value of the function at the beginning the same as the value of the function at the end? So let's find out. That guy, take away that guy, add 4. What's that give me? 6 and 4 is 10, 13. And 3 lots of 3 squared, take away 6 lots of 3. Plus 4. 27, 31. Yep. There we go. None of that really gets written into WebAssign, but you kind of do it. So continuous, differentiable, and it starts and finishes at the same height. So that means there is some place where the derivative is 0. So 6x take away 6 is 0. You could do it in my head. X equals 1. And the place where it is 0 is 1. And yeah, it is correct, isn't it? It's in that interval. They call this special number C. So in WebAssign, all you do is you put C equals 1 in. Now, if there was 2 places, let's say C equals 1 and 2, then you do that. And if, if Rolle's theorem doesn't work, if Rolle's theorem doesn't hold, if the function's not continuous or it's not differentiable, then that's kind of the end of the question and you don't really do anything. So let me show you a situation where you can't use Rolle's theorem. That function in the interval -8 to 8. Right. Definitely continuous. If I differentiate this function, I multiply by the power and I reduce the power by 1. I get that fella. Is there any value of x where this derivative would be undefined? This derivative, this function here, is there any value of x where you couldn't get its answer as a number? I can see one, so what is it? 0, I see my... Since this function is not differentiable between -8 and 8. And that just means there only needs to be one point, in this case, that point. Rolle's theorem can't be used. And so when it does that, C equals, ends up being it doesn't exist in this case. Let's do one last one of Rolle's theorem. When you look at this function, is this function continuous everywhere? Does x plus 1 over x have any problems? It does. Doesn't it have a problem at 0? But does it have any problems in the interval 166? No, it doesn't, so it's okay. It only needs to be continuous and differentiable in the interval. It doesn't need to be continuous and differentiable everywhere, right? So as long as it's okay for values of x between here and here, it's okay for Rolle's theorem. So it's continuous. If I do its derivative, you get 1. I'll call that x to the -1. And so you end up with that guy. Is this differentiable? Is this function differentiable everywhere? Well, it has a problem at 0 again, but 0 doesn't matter because it's not an interval, so it's good. The value of the function at 1/6 ends up being 1/6 plus that guy, which is 6 and a 6, which is 37/6. And the value of the function at 6 is essentially the same thing. So does it have the property that the value of the function at the start and at the end are the same number? Yes, it does. So this function, this weird one here, you can use Rolle's theorem. So we can take the derivative, and there's going to be some place where the derivative is 0. And then all we need to do is find what those guys are and stick them in a box called C. Right, if I wanted to solve this equation, there's lots of ways to do it. One of the ways is that, cross multiply, and technically I get plus or minus 1, but my interval is only from here to here, so the only one I'm using is 1. So what Rolle's theorem allows us to do, it allows us to verify that there's a solution in the first place. It tells us, yeah, you'll be able to get some place where the derivative is 0. And so you're not wasting your time if you go looking for it. Not sure how vitally important that is, but that's what Rolle's theorem allows us to do. And you can only use it when there are certain things that have to be true. The function has to be continuous in this interval. Its derivative has to exist in this interval. And the value of the function at the start and at the finish has to be the same number. If all of those conditions are met, then you can use Rolle's theorem, and it says, look, you're guaranteed to get some place in that interval where the derivative is 0. Any questions about Rolle's theorem? Does it seem pretty okay? Yeah. So there is a second guy that we're going to do, actually the one that this homework is called after. And he's called the mean value theorem. Let me do him again. I think he deserves a big diagram. Now, mean value theorem. Now took the idea of Rolle's theorem and they just extended it a little bit. Suppose I have a function a that starts off at a height of f of a, and then it finishes at b, and it finishes off at a guy called f of b, and it's a nice continuous differentiable function. Just a nice curve, nothing weird going on. So it's differentiable and it's continuous, just like Rolle's theorem. So the conditions for you to be able to do the mean value theorem is that f of x has to be continuous in the interval from a to b, and f of x has to be differentiable in the interval from a to b. And that's it. That's the only things that need to be true. So what does the mean value theorem say? Well, it says if you join a line from the start to the finish, which is this green line, then I'll write it down in English. The mean value theorem says there will exist at least one number c between a and b such that the derivative of the function at c is equal to f of b take away f of a over b take away a. Right, well, you see that green line that I've just drawn? If you add a little guy going this way and another little guy going that way, isn't the rise f of b take away f of a, and isn't the run b minus a? In other words, this thing here is the slope of the line joining the start to the finish. And what the mean value theorem says is there is guaranteed to be some place on this curve that's got the exact same slope as that line. And if I was a guessing person, it's probably about here somewhere and probably about here somewhere. So there's at least one place, we'll call it C, but there could be two or three. So I can imagine if you start at some place and finish at some place. What that is kind of saying is that isn't there guaranteed to be some point in a curve that's got the same number as the average slope, right? The slope from the start to the finish, right? The average slope. Now, if this was a distance time chart, that would say there's at least some place on your journey where you are doing the same as your average speed. So see if I go from Bremerton to Poulsbo and my average speed is 50 miles an hour, the mean value theorem says it's guaranteed that somewhere in that journey, at least one place, I'm doing exactly 50 miles an hour. Do you know, well, they probably don't do it in America, but they do it in Britain. Do you know on motorways in Britain, they have speed cameras? They have those special cameras that record your license plate. And in Britain, you have to have a license plate on the front and back of your car, but they record the rear license plate of your car. And then in another bridge later on, they have another camera that takes it, and they have a computer, and the computer finds your average speed between the first bridge and the second bridge. And if that average speed is greater than the speed limit, you have broken the speed limit. Now, what some people thought they could do is they'd come to a bridge and they'd slow down to 70 miles an hour so that the camera would take a picture of them doing 70. And then they'd speed up. And then 4 miles later, when they hit the next bridge, they slowed down again so they'd still be doing 70 miles an hour. But what the camera did wasn't recording your speed at the bridges. It was recording your average speed, which is how long did it take you to go from the first bridge to the second bridge, divided by the timestamp. Now, if your average speed is 90 miles an hour, according to the mean value theorem, didn't you have to do 90 mile an hour at least once? Even if you're only doing 70 at the first bridge and 70 at the last bridge, didn't you have to do at least 90 in the middle somewhere? So somewhere you were breaking the speed limit, and they don't need to prove exactly where you were doing the breaking of the speed limit. Don't they only need to show, to show that you were doing it? And being a nice country, Britain, the computer sent you a speeding ticket because your license plate is registered under your name and your address is registered under your name. So isn't that a cool way of making lots of money? Just set up these cameras on the bridges. Don't put them in all the bridges. Just put them in enough and you catch lots of people. Right, back to this story then. How does that apply as a question? Well, let's take a function. 3x squared, take away 4x plus 2. And let's say I'm interested in the interval from 1 to 3. We'll assume that that's continuous and differentiable, and so we can use the mean value theorem. F of A is the value of the function at -1. So that's 3, add 4, that's 7, add 2, that's 9. We find the value of the function at B, in this case, that's 3. 3 lots of 3 squared are 9, 27, 29, take away 12, 29 take away 12, 17. F of B, take away F of A over B minus A is 17, take away 9 over 3, take away -1, which is 8 over 4, which is 2. According to the mean value theorem, there has to be some value, some number C, whose derivative then is 2. This guy's derivative is 6x take away 4. That gets me 6x equals 6, and that gives me x equals 1. So there's the C that they're looking for. And just to back it up, isn't that inside the interval -1 to 3? So for this function, starting at -1 to 3, the slope of joining the start point to the finish point is a slope of 2. And the mean value theorem says there is somewhere in that curve, in this case it ends up being at 1, where the slope of the curve is also going to be the average of 2, the mean value theorem. Are we cool with that? Let's do one. What one will I do? This one. I have a function, a cubic. It's going to be my A and my B. It's continuous and differentiable, so I can use the mean value theorem. The value of the function at the start is -8, that's 1, and that's 7. The value of the function at the end is 8 and 9 is 17, take away 6 is 11. The average slope from start to finish, which is this guy, is the value of the function at 11, take away value of the function at 2, I should say. Take away the value of the function at -2. And what do we get? 11 take away 7 over, oh, this is getting boring. 1. So according to the mean value theorem, there should be some place where the derivative is 1. And this fella is 3x squared take away 3. When I solve for it, technically I get plus or minus the square root of 4/3. That gets me 2 over root 3. So there's going to be 2 places, -2 over root 3 and +2 over root 3. And the reason why they're going to be 2 places is that both those numbers are in the interval. Suppose one of these numbers was 5, then I wouldn't use it. Right, I'd only use the one, whatever one it is that's in that interval. Here we have 2 good values. It's quite mechanical, isn't it? You don't really need to think much. You're basically just going to use the mean value theorem to find some point in that interval whose derivative is the same as the average slope. Okay, this is the last guy, and then we'll talk about our test. This function is continuous and differentiable on the interval 1 to 3. It does have problems at 0, but 0 is not here, so I don't care about it. The value of the function at the start is a natural log of 1, which is 0. The value of the function at the end is log 3. The average slope from the start to the finish, which is what this guy is calculating, is log of 3 take away 0 over 3 take away 1, which ends up being slightly ugly looking. That guy. So since we can use the mean value theorem, there's going to be some place where the derivative is equal to this ugly guy. The derivative of a log function is 1 over x.
Excuse me, Professor. I think that
Yes.
is supposed to be a 2 because you go 3 minus 1.
Well caught. So I know cross multiply probably. Too much in a hurry for my own good. There, that's the guy you're going to call C in WebAssign. Right, the value of x where it happens is called C. And oh good, it's the right answer. So welcome. So if I gave you a function in an interval, do you feel comfortable you could do the mean value theorem, which is basically find out what number the average slope is, and then find when the derivative is equal to that. And when you find the value or values of x where that's true, just call them C and stick them in the box. Any questions about that before we call it good? In the big scheme of things, was this probably quite an easy, quick section to do? Right. Not a lot happened. Okay. I hope that's true for you. Oh, to use this here. And let's just spend a few moments once I get my stuff sorted out. Right, well, we all should know, I think I've mentioned it at least a couple of times, that Monday's a holiday, and so your test is going to be on Tuesday. The usual rules apply. Your test is going to be as a PDF, and it's going to appear. I just hit the wrong button there. Did not. There we go. Until I don't multitask. So now I'm ready to kind of share with you what it's about. A lot of topics in this one, but we don't have enough time to give you questions on a lot of topics. So let's see what it's about. Logarithmic differentiation, right? Differentiating logs and inverse trig functions. Related rates, and rates of change. The linear approximation function, which has now been extended, so you can have until Monday midnight to do the extra credit. If you don't do the extra credit, I strongly suggest you watch the video just so you can do 310. Max and min, which we've done, and finally mean value theorem. So there are 6 possible topics, but you're only going to get tested on 4. So there are going to be 4 questions. And you know how Murphy's law works. See the 2 that you don't study for? They're the 2 that out of the 4 that's going to be in the test. Right? So work on the assumption that all of them and any of them could end up being in your test. And that's the safest place to be. You are allowed to use any notes and all that good stuff. WebAssign will be locked out and most of Canvas will be disappeared. So the only thing that I'll leave, apart from the obvious thing, which is going to be the test itself, is that Desmos will be there because you may want to use it from time to time. Any questions? We all used to be the test work now, right? So just stick to the rules.
Can you repeat that last section?
I'm trying to remember what I said in the last section.
3.6, 3.9, 310, and...
Oh, they're all on the screen. So if you can't see the screen, it's 3.6 to 4.2.
Check.
Right, so that is 6 sections, starting at 3.6, finishing at 4.2, but only 4 of those will be examined. So you might be really, really good at maximum and minimums and never get a question. And that is not a hint. I have,
Okay.
I have not made the test yet, so I don't even know myself what I'll do. To be honest, I'll probably do a question for each, and then I'll figure out which one or which 2 to drop. Right. No, for whatever reason, sometimes time issues, and sometimes just because I like another question better. So usual rules apply. Make sure that you don't cheat. Our Zoom meeting will be the same as always, and you get half an hour from the end of the test until it is ready to be uploaded. There's a fair amount of wiggle room in that half hour. So if you're finishing off a question and time kind of is up, you still have, hopefully you've written the question down at least, you still have the time to finish it and do the pictures. I think most people are okay now at using the camera. You might want to check, a couple of you had trouble with darkness. You know, it came up very light. I suggest also you use a pen. Pencils don't tend to work well. They tend to be very faint. So I would probably do that. Oh, and show every bit of working under the sun because you want partial credit, right? Say hi and bye-bye. And I'll hang about for any questions that you might want to just ask on your own.
Thank you.
You're welcome. Bye-bye, guys. See you Tuesday.
Weekend. See ya.
I don't know if you have time for this, but if you wouldn't mind, I could take a picture of each of your pages and notes. Because,
I can do that for you. I'll set them up right now for you.
All right.
Okay. Here's one of them. Oh, you can't see it yet. I'll try and put them in numerical order as I go through them. Okay, these 2 pages, and the one on the left is Rolle's theorem, and the one on the right is called the mean value theorem. And we've been, these are the 2 theorems that are used in this section. So you tell me when you've got a good.
Yeah, I got that.
Got that? Right. So what we then basically did is we did some examples of those questions. So here are 2. And these are similar to questions 3 and 5 in the homework. Essentially, you don't actually prove it, you just say it because it's obvious that this function is continuous and differentiable. Any nice curve is, right? So if you get a nice curve, it's probably going to do it. You don't want vertical asymptotes and you don't want cusps, but none of them are happening here, so it's not a problem.
Okay.
And so this is Rolle's theorem. So you've shown that it's continuous and differentiable. And for Rolle's theorem, the value of the function at the beginning, which is in this case at x is -4, and at the end, which in this case is x equals 4, they have to be the same number. And if they are, you can use Rolle's theorem. And Rolle's theorem says the derivative is going to be 0 somewhere. And there ends up being 2 solutions, but only one is usable. The x equals 4 doesn't get used because Rolle's theorem and so does the mean value theorem say you can't really be sure that the ends work, so just don't use them.
Oh, okay.
And this here is question 5, which is essentially the same as that. In this particular case, that 2 didn't exist. I was just saying that's what you would have done if there had been 2 answers.
Oh, okay.
Are you good with those 2?
Yeah, those are good.
Okay, so we then did, oops, daisy. Then did this one. That's that top one first. So I'll cover this up. And this one was to show you that Rolle's theorem doesn't always work. You can't always use it. And this function is continuous, but it is not differentiable at 0. And 0 happens to be in the interval. So you can't use Rolle's theorem. That's essentially what that one was saying. And we've got 6.
Yep.
Question 8. Here is a function. This function has a problem at 0 as well, but you can use Rolle's theorem. And the reason for it is that although this derivative has a problem at 0, 0 is not in the interval that we're interested in. So Rolle's theorem says, as long as it's okay in the interval, it's okay to use it. It could have problems somewhere else, but we don't care about those. And if you solve, which you can, Rolle's theorem says, there we go. That's what it looks like. That the solution happens to be at 1. And that's Rolle's theorem. Then we went and did the mean value theorem. Now, the mean value theorem is really an extension of Rolle's theorem. What it says is that when you're doing a function, if it's continuous and differentiable, but the start and finish values are different as they are here, you can find the average change, right? The average slope from the start to the finish. That's what this is. And whatever that number is, the mean value theorem says that the derivative will equal the average value. So Rolle's theorem says the derivative is guaranteed to be 0. The mean value theorem just says that the derivative is guaranteed to be equal to its average value, which means whatever this is. And in this case, this function is continuous and differentiable. So we can use the mean value theorem, and we're trying to prove that the derivative is 1, and we solve it, and there was 2 solutions.